This is a talk called A Tale of Two Asyncs, or because I love incredibly long titles, how language values shape the features we build and the journeys we take to design them. This talk's probably going to end up taking the whole time because, as you can see, I have 166 slides. But I know there is the app where you can ask questions, but this is also on GitHub, and I am a good open source maintainer, and if you ask questions and issues, I will follow up with you. So by way of introduction, my name is Ashley Williams, or as you may know me from the internet, AG Dubs. If you follow me on Twitter, I'm sorry. Follow at your own risk. And I've done a lot of things in my career. For the past 2 years, though thankfully kind of no longer, I was on the Node.js board of directors. And while I was doing that, I worked at this small company called NPM that if you write any sort of JavaScript, you've probably heard of. While I was doing that, I ran an inclusive education program called Node Together, which focused on getting underrepresented folks into programming by teaching them Node. And education is my passion, which is something that's going to come up in this talk. I have worked on TC39 as an invited expert, bringing educational perspectives to the design of the language. But recently, at the beginning of the year, I changed my job over, and I work for a company called Mozilla. And I work on a programming language called Rust, which I did not expect to be so featured in the keynote. How many people here write Rust? How many people would like to try? All right, there we go. That's awesome. So there's a whole bunch of things here that I do. Open source is kind of like a startup. There's lots to do, and you wear many hats. But another thing that came up in the keynote, which is amazing, is currently I'm spending the vast majority of my time building dev tools for compiling Rust into WebAssembly. And so that's what I spend most of my time doing. But when I got into Rust, I started by being a teacher for this program called Rust Bridge, which is a similar inclusive education program as Node Together, getting underrepresented folks into tech by teaching them Rust. And so these are just a couple of these pictures here of Rust Bridge happening. And this is the kind of stuff that truly inspires me about programming languages in general. Sometimes I'll dress up like a crab to teach. So I love teaching programming. And it's because I really love programming languages. And fundamentally, I'm the type of person who loves to think about thinking, particularly the type of thinking that happens when people write code. My degree is not in computer science. My degree is in philosophy and neuroscience. So you can imagine where that thinking about thinking comes in. I went in for film and then leaned in real hard into how do brains. And here I am today talking to you about programming languages. So the goal of this talk today is to explore two languages that I love. And you can see here that I write Node.js, and maybe some of the pedants in here might be, that's not a language. Yeah, I get it. I know. I'm up here on the stage. I know that it's a runtime. But my familiarity with JavaScript is primarily through Node. And so I'm going to talk a lot about Node, but we'll also talk a little bit about JavaScript. So this wouldn't be a proper Ashley Williams talk, if you've ever seen me before, if I didn't give you a little bit of philosophy. So let's get right into it. So one of my favorite concepts in philosophy is this idea of genealogy, which is a historical technique which is primarily looking at how concepts emerge from the historical context that they exist in. And so here's my lovely bushy mustache friend, Friedrich Nietzsche. And one of the things that he says is that a genealogy often attempts to look beyond the discourse into the question of the conditions of possibility. What are the things that made it so that this type of conversation could emerge at this point in time? And so another fellow who was incredibly interested in this topic was this gentleman here, Michel Foucault. And so he says this, he says, the point of a genealogical analysis is to show that a given system of thought was the result of contingent turns of history, not the outcome of rationally inevitable trends. And we are going to circle back to this, so do keep it in mind. Now, I was making this talk and I tweeted about it, and one of my friends said, that is the nerdiest way to say shit happens I've ever seen. She's not wrong. But the thing that I'm really excited about with genealogy is that it's an investigation into elements which we tend to feel are without history. And programming languages fit this well. Programming languages are deeply complex historical artifacts and agents, yet we rarely think of them as such. And so while I'm going to be talking about asynchronous features, I'll be talking about Node, JavaScript, and Rust, fundamentally, what I want to talk about is how we can view these things as historical artifacts. So another one of my favorite authors, and if you've ever looking for a book, The Structure of Scientific Revolutions by Thomas Kuhn really completely changed the way I think. And in that book he says, scientists work from models acquired through education and literature, often without quite knowing or needing to know what characteristics have given these models the status of community paradigms. And so here we need to question, like, we do so many things, but why? What are the origins of these things? And that was a question that throughout university I was obsessed with in my philosophy classes. What are the origins? And so a great origin question, particularly as a teacher, is to ask this question, what is the best first programming language? And if you Google this question, you'll find a white paper, and it has this fantastically obtuse diagram. Clearly you can tell what the best programming language is from this. But this is a question that we'll also come back to. So inevitably when you ask what is the best anything, it's a trap. Even though we know it's a trap, we often are happy to argue at length about this kind of thing. And one of the words that we tend to say when we argue about this is this idea of the best tool for the job. How many people have found themselves saying best tool for the job? All right, I feel like people not raising their hand are just not participating, because this is just something that happens all the time. And when we ask about what is the best tool for the job, we have to start asking, what do tools want to do? And so the question I'm here to really ask today is, what do programming languages want? And this is a question I don't think we ask ourselves nearly as much as we should. So when I was investigating this, probably around 3 years back, I came across this idea of programming language paradigms. And so a programming paradigm is an approach to programming a computer based on mathematical theory or a set of coherent principles. Each paradigm supports a set of concepts that makes it best for a certain kind of problem. So when we talk about best tool for the job, what we start looking at is this idea of paradigms. So I love this because there's a delightful computer scientist named Peter Van Roy, who is clearly a very serious individual. And he's written extensively about programming paradigms, and he was really some of my foundational CS learning, reading all of his papers. And so he came up with this idea of the paradigm paradox, which is a paradox to even attempt to pronounce. But it's the idea that more is not better or worse than less, just different. And so when we're looking at tools, the best tools for the job, all right, how do we have programs or tools that solve problems? And are the tools that solve more problems better, or are they worse? And here he says, no, they're actually equivalent. There's a very interesting play between those ideas. And so he has made another fantastic diagram. I guess computer scientists love making like completely inscrutable diagrams, but at least this one's rainbow, so we have that. And in this diagram, he attempts to map out a ton of programming languages and the types of paradigms they fit in, or perhaps the multiple paradigms they tend to fit. And so when we're thinking about genealogy, addressing the types of paradigms that programming languages fill and then looking at that in a historical context is a way we can start approaching an idea of a genealogy of programming languages. So to get a little bit more concrete at this point, I like to ask the question, what type of tool or language? I love calling languages tools because it's so easy to forget that that's really all they are. What type of tool does Node.js want to be? And so we're lucky here because there's actually a little bit of design work that actually happened and that you can go and find. A lot of the research done about what types of tools languages want to be is incredibly difficult to find. Now, unfortunately, the thing that's frustrating about trying to figure out what does Node want to be is that you have to go back pretty far. So this is Ryan Dahl, the creator of Node, when he is originally, oh yeah, the captions are there for your pleasure. He announced Node in 2012, or no, 2009, but then this was republished in 2012. And the goal of Node was that he fundamentally believed that the way we were thinking about I/O was not only wrong, but was making things incredibly difficult. And so just to step back and think about it for a second, a lot of us are programmers here in the room, and there's this idea of asynchronous programming, and it's something that feels kind of ubiquitous. But asynchronous programming is defined as the idea of making it possible to express waiting for long-running actions without freezing the program during these actions. And I like putting this out only because this is a quote from Marijn Haverbeek's eloquent JavaScript. And interestingly enough, Marijn actually worked on the original Rust way, way, way back in the day. Our computer science worlds are so, so small. But with all of the work that we're doing in asynchronous programming regarding syntax that's able to express it, I think we often forget that really all asynchronous programming is about is the idea that what is the software doing while it queries the database? And in this situation, the answer is nothing. And asynchronous programming goes, well, that's a big problem. All right, we need to change that. And so fundamentally what we're doing as we program asynchronous features is really just handling this one very small core concept. And it seems small now, but this actually was an incredible problem. How many people here know what the C10K problem is? All right, so I won't go through and read this all, but the idea is that it turned out that sometimes, before Hacker News and stuff like this, there was this website called Slashdot, and sometimes people's blog posts ended up on it. And they got so popular that they would just completely crash the servers that they were on. You couldn't visit them anymore because our asynchronous story, our concurrency story, was absolutely terrible. So we would say things like, it's time for web servers to handle 10,000 clients simultaneously, don't you think? Wow. Yeah, after all, the web is a big place right now, and it's only gotten so much larger. And so not too long ago, this was published in 1999, it's not too long ago that this was actually an incredibly serious problem. And so we started coming up with ways to solve this problem. And the first problem, or the first solution we came up with was this idea of threads, which is demonstrated incredibly scientifically right here. And so Ryan Dahl was incredibly frustrated with this solution. And here he says, threaded concurrency is a leaky abstraction. It creates pains. You have memory problems. It's hard to think about. It is not a good abstraction for what is happening on your computer. And this is why he thought this. It's interesting to think, all right, so the whole goal of Node was like, oh my gosh, asynchronous I/O needs to be a first-class citizen in this language. In fact, it was the driving design decision. And so it's because at the time, what we were dealing with when we were thinking about server-side technologies and concurrency was using Nginx and Apache. And so like many benchmarks, the paper that gives this lovely graph, like, I don't know, dubious at best. But fundamentally what this describes is that Nginx and Apache can both support a whole bunch of concurrent connections. And that's awesome. But there was a bit of a problem, which is that as the concurrent connections grow, so did the memory usage. And this is where we ended up when we were having all sorts of problems with Slashdot and the blog post becoming incredibly popular. So the state of asynchronous I/O as Node was emerging was bad. He even talks a bit about Ruby, and like Ruby was attempting to do this with Event Machine and stuff. But even then, that existed in the ecosystem, and there was many different solutions, and then trying to get the ecosystem to play well together was incredibly difficult. So Node emerged as we want one solution, and we want it to be the primary design value. And so this is because threads are expensive, and it was like, I don't want threads to be the design solution. And so with that came Node. And Node was based on this pattern called the reactor pattern. And so I did some research, and this is the original diagram from the paper. And you might be more familiar with this pattern because of this lovely thing called libuv. How many people here know about this unicorn dinosaur? It's a cool logo. I'm glad we have animal logos in tech. But fundamentally what this is the Node.js event loop. And I think that this is really interesting because fundamentally a lot of people don't understand that the event loop is actually a single-threaded scripting language for still fundamentally a multi-threaded system. But it was adding this abstraction that made it significantly easier for folks to reason about and be able to express programs. And so in his talk, and he does regret this at this point, he goes, callbacks is how I/O should work. And if you follow any sort of Node or JavaScript technologies today, you'll know that callbacks might have been at least maybe a little bit of a mistake. And we've definitely developed our things before that. But fundamentally, this idea of callbacks was really the design decision of Node. And this was really great because Node was really trying to get JavaScript onto the server. And so JavaScript was designed specifically to be used with an event loop. And the culture of JavaScript was already geared towards evented programming. And so to kind of circle up on the answer to our question, what Node.js wants is Node.js wants to provide a purely evented, non-blocking infrastructure to script highly concurrent programs. And that's pretty awesome. It's great to have a sentence where you can kind of sum up, okay, this is what this tool wants. So when you ask yourself, what should I use Node for? If you want to write a program like this is the program that Node was designed to express. And there were a couple other design goals involved in there, but it's awesome that these design goals were written down. If you actually go to the Node.js GitHub repo at this moment, it's really impossible to find these goals. And the importance of these goals is going to become a theme throughout this talk. So evented programming is the primary paradigm for Node.js. And so given that Node.js is so deeply close to JavaScript, because JavaScript is fundamentally the language, with ECMAScript being the spec underneath, we have to ask ourselves, OK, so Node as a runtime has a really clear goal. But what type of language does JavaScript want to be? Now, we all know the story that JavaScript was written in, what, 10 days? I don't know. It's a short amount of time. It was rushed. And it was really just designed so that you could have a little bit of interaction on a website, even after the website's pages had been loaded in a client. So I did some digging, and this is the best I could find on what type of language JavaScript wants to be. In the spec, it says ECMAScript syntax is relaxed to enable it to serve as an easy-to-use scripting language. Now, this is the best definition of what JavaScript wants to be that I can find in the spec. And again, I do not believe that the people currently designing the language are returning to this statement as they evaluate features moving forward. I don't think I would describe anything in JavaScript maybe at the moment, at least as relaxed, though obviously the word relaxed can mean many things in this context. So we've talked a little bit about Node and JavaScript, and so now I want to bring up this idea of Rust. So I currently work on Rust now, and because I'm on the core team, this is an incredibly important question to us. In fact, we have a repo right now where we're working on coming up with the language to answer this question. But for a really long time, when we say, what type of language does Rust want to be, we've said this. Rust is a systems programming language that runs blazingly fast, prevents seg faults, and guarantees thread safety. And unfortunately, when most people read this, they hear this. And that's a real bummer, because what a language wants to be is telling people how to use it. And so I asked you at the beginning of this talk how many people write Rust, how many people are interested. There were way more people interested than people actually writing it. And I think it's because a lot of people are like, Rust seems real cool, but what do with Rust? I don't know what to write. And it's a good question, and it's something that we're actively thinking about and working on. So to go a little back in history, Rust was originally designed as a systems-level language with the purpose of wanting to write something that was safer and more maintainable than C++, which was what Firefox is currently written in. So Mozilla was like, this code, it is taking way too long to develop on. We're having all these bugs. We need something that's safer and more maintainable. And by maintainable, they mean I want to be able to express a safe program without tricks, because tricks are those spots in your code where the comment is longer than the code block itself, and it's incredibly brittle, and you come back a day later and you still don't know what it is that you wrote. And so what I like to say with Rust is that, we're a systems language. We're close to the metal. And this is another lovely thing that almost no one ever really means. There's fun parts of it where, like Rust, it's like a fungus that grows on metal. That's how close we are. But that still doesn't really help people use it. So a little bit about Rust if you don't know about it. We don't have a runtime, we don't have a garbage collector, we don't have segfaults, and we have static typing. And this is what we generally do to serve that goal purpose that I just stated. And so Lee Bailey gave a lovely presentation a bit back at a RustConf where they drew cartoons talking about how Rust works. And this is the anthropomorphized version of the compiler, a referee that tells you no, because the safest program is one that does not compile. It's true. But while that was a pretty aggro-looking compiler, I tend to think of the compiler as kind of my buddy. I like programming in Rust because I am constantly pair programming. And this was a small conversation I had where the Rust compiler helps me eliminate a whole bunch of the cognitive overhead I have when I am programming. I can kind of just go in and refactor something. I don't even check my imports or any of that. I'll just type in the code I want and then run the compiler, and the compiler will be like, do this, this, and this, and it's fantastic. We have error messages where you can often just cut and paste the suggestion and it works. It's really a great thing, and this is one of the things I love about Rust. And so with that, I kind of have a different definition of Rust. I like to say, Rust is a systems programming language designed to empower all different types of developers to write all kinds of fast, safe code. A lot of people ask, you have a brand new programming language, all right? We have a bunch of developers who are already using languages. Is the idea that you're trying to convert, like, say, C++ developers to Rust? And there is an element of that, but Rust's real goal is to take folks who weren't already systems programmers and make them that. It's additive. It's like, let's go find all of the people who weren't being able to express these types of programs, and let's give them a tool that will let them do that. So part of the way we did this is through first-class package management. We have this fantastic tool called Cargo. Cargo is close to my heart because I came from NPM, and Cargo learns a lot of things from NPM, and if you're worried about that, trust me, we took the good things and not the bad things. Opinions, dev tools are full of them. But Cargo is fantastic. We have crates.io, so you can use lots of libraries. And this is a very large cell over a lot of previous systems programming languages which don't have these type of tools to make developer experience much better. And so in 2018, we wrote a roadmap. And this is something that the language does every year, and it's to describe and work with the community to come up with the goals that we want. And so in 2018, we added this idea of domain working groups, which is kind of to answer this question, well, what the heck should I write in Rust? We know this is a problem. And so we came up with 4 working groups: networking services, WebAssembly, CLI apps, and embedded devices. And so this has been working well, and it's coming up to our shipping of an edition in December. So the culmination of all of the work of these groups is coming up really, really quick. And so what I want to talk today is about this idea that Rust wants to be a first-class server-side language. Now that's kind of interesting for a systems-level language. And so in Rust, towards our goal of being able to be a server-side language, we knew that asynchronous features were going to be incredibly important. But asynchronous features, unlike Node, were not the foundational value of Rust. The real foundational design value of Rust was this idea of memory safety. That's really what we focused on first. But with the growth of the web, the pervasiveness of it, with the idea that so many applications are web-based, we wanted to be able to be present there, and we believe that Rust will be good about it. Remember that one of the biggest problems that Ryan saw before he invented Node was memory usage, and even in Node, I know my friends on the Node TSC are like, the garbage collector is my least favorite person. Oh my gosh, they're constantly fighting memory errors. And so we're like, with our memory safety values, we could be a really interesting language for the server. And so we proceeded to start designing asynchronous features. And so Mio is the foundation of that, Metal.io. This metal thing comes up all the time. It's incredibly frustrating. But that's to say that it's incredibly low level. But one thing to note is that Mio is not in our standard library. This is something that is existing out in the ecosystem. And so Mio is the bottom layer, and then we have this idea of futures kind of on the top. And so I like to say futures are promises, but not exactly. So if you are more familiar with promises, futures might be a little bit, there's a mental model there that you can use, and there are a couple of differences. And we are adding some just very small pieces, particularly the types of futures, to the standard library in order to be able to serve this goal of being a server-side language. And so when you put futures and Mio together, fundamentally our asynchronous paradigm at the moment is this idea of Tokio. And you'll see that these all say I/O at the end, but the names are like a bit inscrutable, and trying to figure these all out together can be a bit difficult. So you can kind of understand that Tokio is when you take this top-level kind of futures, promises abstraction and put it on top of this metal I/O layer. And when we put those together, we get Tokio. And so that beautiful Node.js system diagram, which was good, I decided I love, editing things in MS Paint. And so revealing to you today the Rust system. Yeah, so this is kind of a haphazard diagram, but the idea here is to try and talk about the fact that we took a lot of influence from Node.js when we started approaching asynchronous language design in Rust. And so here you can see we don't have a runtime, but we've got the Rust, futures, and we have tasks, and we have this idea of the Tokio reactor. Now, all of these are very cool, but remembering that Rust is a systems-level language that allows you all of this configuration and really wants you to have memory safety, even though this is incredibly close to Node. And when I endeavored to start writing some asynchronous Rust code, which in the long run will look like this, where they sync and await, one thing that's fascinating for my very first experiment was I wrote a bunch of asynchronous Rust code. It passed the compiler finally, it passed all of the lints, and I ran the program, and nothing happened. And I was like, what? No, it's Rust. If it compiles, it should work. What's going on? And that is because starting an event loop was something that I fundamentally understood to be just implicit. I'm a Node developer. It's there. I know the event loop is there. But here in Rust, it wasn't. It turns out that the one step I had missed was actually starting an event loop. And so that's an interesting thing. And we realized, and one of the biggest frustrating parts of our asynchronous story in Rust is so many people come to Rust with different ideas of asynchronous program expression. We all are bringing different things to the table. And so creating an ergonomic experience for everyone is incredibly difficult. So that's a bunch to say about Rust and it wanting to do some asynchronous stuff, but I have another question. This first thing, everyone was like, yeah, of course, Rust wants to be a first-class server-side language. But I want to ask, should it? That's a really interesting question. Why should we be writing web services in Rust? And that's kind of a question, like a systems-level language, should we really be writing a web service in that? Should you write a web service with a language that was designed to write a browser? I don't know, it's interesting. So as I said before, Rust was originally designed to replace C++ in Firefox here. And there's kind of an interesting illusion here, like a systems-level programming language. Usually the first thing you think to write in a systems-level language is an operating system. And what are browsers if not kind of their own type of operating system? And so Firefox Quantum shipped with the first-of-kind parallelized style system Stylo last year, and it was incredibly successful. Use Firefox. It's great. And fundamentally, this was because Rust has this ability to be incredibly maintainable, and it's incredibly expressive. So these are some cartoons from Julia Evans, and if you love code cartoons, you should check hers out. This is an incredibly not scientific diagram of your program workingness over time. But the idea here is that Rust makes improbable programs possible, right? And the idea is that it's empowering. And so why should we take this type of power away from people who are looking to write web services? I think there's a whole bunch of web services that have yet to be written, and it's because there's not yet been a language to be able to express them. So, and again, this whole idea of empowering for a wide variety of people who might not otherwise consider themselves systems programmers. I want web developers to be systems programmers, and so does Rust. And so the fundamental answer to this question is yes, I do. I do absolutely think that you should do this, and so does Rust. And fundamentally, this comes down to these ideas of memory. I think that as we have lots of conversations about web development, we tend to have a lot of conversations about both concurrency and memory. And Rust has this idea of finding contradictions and saying, no, I don't believe that is a fundamental trade-off. I think that we can write a language that allows you to do all three of these things. You don't have to pick just two. Now here's the trick though. the real trick here is productivity. Productivity is an incredibly difficult concept, and it comes down to developer experience. Have you had this developer experience? I have. So, to jump into something that seems like it's completely different, to quote Douglas Adams, the history of every major galactic civilization tends to pass through 3 distinct and recognizable phases, those of survival, inquiry, and sophistication, otherwise known as the how, the why, and the where phases. For instance, the first phase is characterized by the question, how can we eat? The second, why do we eat? And the third, where shall we have lunch? All right, so now why am I talking about lunch and Douglas Adams right now? And it's because we have to realize that while programming languages are historical, the people who are using them are also historical. And so people who are using our programming languages go through stages of learning. And it turns out that while as we design concepts and syntax for them, these are incredibly important. And so this is from a paper by Terence Tao, who's actually a mathematician. And he defines 3 stages of learning. The pre-rigorous, where you kind of blindly apply formalism and you're just very intuitive, kind of feeling around in a dark room. The second is quite different from that. It's incredibly rigorous, where you kind of have this intense, proper application of formalism. Like, yes, I will do this, and I know these are the rules. And then finally, this idea of sophistication, or the post-rigorous, is when we kind of return to intuition, greatly informed by the idea of formalism, but we can return back to our mental models and less of the strict specifications of the language itself. And so my friend Dave Herman read this, and he coined it as Strauss-Strup's rule, which is that for new features, new programming concepts, people insist on loud, explicit syntax. Whereas for established features, people want incredibly terse notification. And so you can kind of understand that maybe the beginner or even the advanced person in our previous stages of learning like the loud, explicit syntax. Whereas the people in the middle sort of like this terse notation. They already know the formalisms, and they just want to apply them as quickly as possible. They're the people who really count the number of letters you have to type, which is a whole nother thing. But an example of this in Rust is how we do error handling. So in Rust, we do not have exceptions. We have explicit error types. And you can kind of see how we progressed through. So at first, you can see here we have a match on a result type, where either it's OK or you pass an error. But that sure is a lot of code to write for this. And then so after a while, we made it a little bit terser, and we had this try macro. You can see the word try with the exclamation point. And it turns out that even those 4 characters were like a little bit too much. We're like, this is error handling. We all get it. Let's just get on with it. And so now we have this postfix operator called the question mark, which maybe you didn't even see because it's so not loud. And that just propagates an error up to the function that calls it. And so this is an example of us building syntax for this. Now, it would have been incredibly difficult to have introduced question mark first. We couldn't have just released Rust with question mark. There was nobody who was ready for it at that point. But as people moved from the beginning stages to that intermediate stage, their desire for how loud the language should be and how loud the syntax should be changed. And so this is one way that we have kind of historical recursiveness within our language design process. And so this comes down to this idea of the mechanism is not the model. And so Dave Herman writes, I see this a lot in standards and design. As we spend more and more of our time swimming in formalisms like specs, semantics, or implementations, it's easier for us to overlook these fuzzier intuitions. Just like in mathematics, rigorous tools like specs help us be precise. But the mechanism of our designs and the developer's mental model they support are 2 separate things. And oftentimes, and this goes back to Simon Peyton-Jones' keynote yesterday, we focus so much on the technology and not the ideas. And I think we're in an era of language design, at least in very popular language design, that we're losing track of these ideas and intuitions. So interestingly enough, Rust has taken this kind of to the nth degree, where we tend to build features for the survival and sophistication stages. We really are focusing on our ergonomics ideas, on these ideas of developer intuitions. And yeah, this makes the folks in the inquiry stage like incredibly frustrated. And you'll see very soon, I'm going to show some examples of our GitHub conversations, but they are long. But Rust doesn't have all the answers, but one of the things that we are trying to do with language design in Rust is we're trying our best to ask the right questions. And so fundamentally, the real question for Rust is, can Rust achieve the ergonomics and productivity required to make systems level control viable for web development? Web development is hallmarked by these languages that tend to be higher level scripting languages that have high abstractions. It's very easy to be productive in them. Can Rust do that while also giving you that systems level control? It's an open question, and it's the question that will determine the success of Rust, I believe. And so, are we doing it? I don't know. This is Stack Overflow. We have been the most loved programming language for 3 years. I don't know what that means. Does anybody know what that means? But one of the things that I do think is actually a good example of us attempting to succeed is this article by Nick Fitzgerald called Oxidizing Source Maps with Rust and WebAssembly, where he demonstrates that writing a source maps implementation in Rust and then compiling it to WebAssembly was not only significantly faster than the JavaScript, but it was also more consistent. Like, that jump in speed, I think, is way less important than that lack of spread. Look at that consistency and what you can expect. And that's super awesome, and it's incredibly successful. Now, of course, M. Ralph, who also spoke at the conference yesterday, immediately was like, you don't need Rust and WebAssembly to speed up your JavaScript. You don't need to. And he proceeded to give an absolutely fascinating discussion of V8 internals and writing JavaScript with all the tricks to make things go incredibly fast. And I love blog posts like this, but I think he missed the point of what Rust wants to do. And so Nick actually followed up with incredibly polite blog post, but it was called Speed Without Wizardry. And in it he says, the oxidizing article recounts my experience integrating Rust, compiled to WebAssembly, into the source map JavaScript library. Although the JavaScript implementation was originally authored in idiomatic JavaScript style, as we profiled and implemented speed improvements, the code became hard to read and maintain. However, with Rust and its zero-cost abstractions, we found that there was no trade-off between performance and clean code. And so that's the idea. Is like, of course, I mean, you can be fast, but being fast and being able to remain maintainable is incredibly important. And so the question is, how did Rust get to this point? What is Rust trying to do, and what were the processes that helped us lead to this design? And so there's a beautiful talk called Why Wasn't I Consulted? How Rust is Open Source Software by Nico Mitsotakis and Eric Turan, who are on the core team with me. And this is the core team, and we have tons more people. We have around 100 people working on Rust right now. And it comes down to this idea of why wasn't I consulted? And Paul Ford wrote an essay on this and says, why wasn't I consulted is the fundamental question of the web. It is the rule from which other rules are derived. Humans have a fundamental need to be consulted, engaged, and to exercise their knowledge, and thus power, and no other medium that came before has been able to tap into that as effectively. And so when we do consultation Rust style, we are doing everything via an RFC, every major decision, and we consider most things major decisions, even policy decisions. And even people from the core team have to write an RFC to get something into the language. And so we drive it through to a steady state of consensus, and we absolutely insist that all decisions rest on prior public debate. There's no going off into a room and then going back to the thread and saying, we figured it out. We have to hash it out on that issue. And this is actually incredibly radical. And I always read this quote and I'm like, I can't even believe this is true. But the Apache Software Foundation has a very different idea about how to do this language design. They use this thing called lazy consensus, and lazy consensus is this. It means that when you are convinced that you know what the community would like to see happen, you can simply assume that you already have consensus and get on with the work. All right. All right, so we disagree with that. I still can't believe that's real. And so a lot of that has to do with this idea of articulating visions. And the whole idea is this idea of thought leadership. And particularly if you've been in JavaScript for a while, there's tons of discussion of thought leadership. But there's not maybe a lot of actual thought leadership happening. The idea is that you need to expose a way of thinking and inspire communities towards a clear goal. The whole point of getting everyone together is that we have shared values. And making these language decisions is a lot easier when we all share similar values. And in doing this, we can help identify and explain historical themes. And so I'm not going to quote who this was from, but I like the idea that every good work of software starts by scratching a developer's personal itch. And the whole goal of our method is to make everybody itch the same way, because that doesn't sound weird. You know what I mean. But yeah, vision and values happen at a lot of different scales, and having a roadmap process and thus a vision makes it a lot easier to say no. And saying no is incredibly, incredibly important. Now, you might be saying, Ashley, all of this like kumbaya stuff you're talking about, like pluralism, that's all great, but like, doesn't that like kind of really stink? Like, how do you get anything done? So this is our RFCs repo. Took this a little bit a while ago, and you can see the number of comments there. These aren't too bad, but asynchronous features were really interesting because people really cared about this. The asynchronous features are incredibly important, and so you can see the numbers start going up a lot higher, and here, even higher. Just as an aside, GitHub like reactions are not votes. No one votes in Rust, and this is a huge misconception of the crew. But yeah, lots and lots of comments. And so we have problems of scale. RFC threads can get 100 civil, insightful comments in 24 hours. That's after you eliminate all the like weird cruft that every issue gets. And so there's an information overload. And as many people might not actually realize, open source, you think, oh, language design, you need a lot of technical people. No, we desperately need managers. Oh my gosh, we need managers to be able to handle all of these people. And that's because fundamentally, we believe all of these people are what is making us make a better language. We genuinely believe that pluralism is what is going to lead to actually better design. And we've seen this happen multiple times. And so what's the point of me saying all of this? Right? So I think fundamentally that Rust, especially its asynchronous story, would not be the same if it weren't for Node, right? Rust is in part at least a reaction to Node, and Node exists for a very specific reason, and it was a response to the historical and material situation it was written in. However, I think that there are ways that Node and JavaScript can also respond to Rust. Because Node and JavaScript, as I mentioned to you all before, has not re-articulated their goals or audience in a long time. I have dug for this information. I found one private repo that had one README commit with nothing in it. There's a lack of vision here. And this lack of vision can have some serious problems. Like, we are working incredibly hard in open source, but to what end and for who? And this lack of vision can cause a mismatch in expectations. And I'm running out of time, so I'll skip forward to this. But I want to talk about the worst implications of a lack of vision. And so we've talked about this man before, Bjarne Stroustrup, the creator of C++, and he recently wrote an incredibly important article. And in it, he said, most people in Working Group 21 are working independently towards non-shared goals. Individually, many, maybe even most, proposals make sense. Together, they are, obviously, he's not terribly inclusive, insanity, probably means ridiculous, to the point of endangering the future of C++. And the title of his article was Remember the Vasa. And so I will leave you with this story. The Vasa was a Swedish galleon, which is a fancy word for ship, one of the largest and most heavily armed warships of its time. At the beginning of its maiden voyage in 1628, the Vasa sank after only about 1,300 meters driving distance in normal swell due to serious structural instability. And this is because the Vasa was supposed to be this Swedish ship that a bunch of people built incredibly intuitively. If they could find a spot for an extra gun or an extra something, they were just tacking it on there. You could think of it as feature creep out of control. And so in the article, Bjarne says, we need a reasonably coherent language that can be used by ordinary programmers whose main concern is to ship great applications on time. That's the productivity bit right there. All right, so he switches metaphors, I don't know why, but we have now about 150 cooks. That is not a good way to get a tasty and balanced meal. So 150 shipbuilders, not a very good ship. And so he says, we are on the path to something that could destroy C++. We must get off this path. And so this is the idea that without shared vision, we can end up with languages that are the Vasa. All right, and so here's a map. This is about how far it went. And I think we all believe that we want our languages to get a little bit farther than this. So ergonomics and productivity are the determinants by which the success of any programming language will be measured. And in order to get those right, we need our users to be in the room. And so Russ Cox said this about Go, but I think it's really useful for all languages. To make Go successful, we need everyone's help, and everyone isn't here. And in Rust, we're trying our best. We want everyone to be there, all right? And so we return to this idea of the best first programming language. And in that article that had that ridiculous diagram, they said, the major problem caused by the unavailability of feature uniformity, and that feature uniformity means like one way to express one thing, is that the size of the language increases, which in turn results in a longer learning curve. This leads to an increase in the language complexity in terms of the number and type of constructs. Resultantly, a language without feature uniformity usually demands an instructor to teach a subset of the language. A programmer could use that subset to write code, but for reading code, comprehensive knowledge is required. And so this is my final statement here. I'm a little sad that JavaScript is becoming not a great first programming language. And more importantly, I believe that, and I'm genuinely sad because I think if it's true, it likely happened by accident. I don't think it happened on purpose. I think this is happening and continues to happen by accident as a lack of shared vision. And so we had that original relaxed, easy-to-use scripting language vision, but we haven't returned to it. And when I was first reading this spec, I was giving a talk called If You Wish to Learn ES6 from Scratch, You Must First Invent the Universe. And I said this because I genuinely believe this to be true. And now I'm genuinely afraid that that is going away. And so I'll leave you with this. I'd like to see all language communities better articulate their visions. And I'd like to see more requests for feedback, get more people involved. All right? And I'd also like to see a greater visual realization that the artifacts we build are historical artifacts. These things are products of their time, and a time that is certainly going to change. And so it's incredibly important to keep the feedback loop between the designers and the people using the language incredibly small. And this is not fun. You saw those comments on GitHub. Involving lots of people is incredibly hard. And it gets really uncomfortable, and you feel like you're maybe not moving as fast as you could if you could just assume what everyone wanted. But the technology we build is not the product of rationally inevitable trends. You're not going to figure this out in your head by using some sort of proof or theorem. All right? It is the result of contingent turns of history, which means you have to go out into the world and find out what that history is. And history is going to move forward, and we need to be prioritizing the work of understanding that history, and I genuinely believe that we are not. So I am excited, though, because it's the type of work I love to do, and it is the work to be done, and I hope more folks join us. Thanks.